Good morning, everybody. Hope you all had a lovely evening, and thank you for joining us in the My Tutor online school. This morning we have a GCSE Physics session on the generator and a motor effect. And if you're new to the online school, then welcome. It will be an hour's long session, 45 minutes of content being taught to you by the tutor, and then 15 minutes of questions at the end. And it will be recorded, so you'll be able to watch it back when you want in your spare time. And this session, like all our physics sessions, led by our tutor Preshayla, who's done lots of tutoring with us. It's her 4th year as a tutor, and she studies physics at Loughborough University. So I'm going to hand over to Preshayla to run through what you'll cover and also to deliver the content for you.
Cool. Okay, so today we're going to be talking about the motor and generator effect. So we're going to be talking about how to define the motor effect and this little rule that we have called Fleming's left-hand rule. Then we're going to understand how speakers and electric motors employ the motor effect. Then we're going to know how to define the generator effect, note how to increase the induced potential in the generator effect and how to change the direction of it, and then understand the applications of the generator effect to an AC and DC motor. Okay, so we're just going to start with a quick summary of yesterday's webinar, like always. So yesterday we talked about magnets, their poles, and how to draw a magnetic field with magnetic field lines, the rules that we have for magnetic field lines, and which way they point. Then we talked about how can we plot a magnetic field if we had no idea what it looked like. Well, we can use a compass to do that. So we said that we use small plotting compasses and we put them around the magnet, and then we looked at what way the arrows were facing, and that told us the direction of the magnetic field. Then we went on to talk about how current carrying wires, so any wire that has a current flowing through it, so is connected to a battery or a cell, has a magnetic field around it. So this flow of electrons in our current creates a magnetic field. Then we went on to talk about how we can work out which way that magnetic field goes. So it was the thumbs up rule or the right hand grip rule, and you point your thumb in the direction of the current, so that could be up or down or left or right, and the way that your fingers curl round is the way that the magnetic field goes. Then we went on to talk about F equals BIL, which we're going to cover a little bit more today in a little bit more depth, but basically what that means is the force on a conductor equals the magnetic flux density times current times length. Then we went on to talk about solenoids. So a solenoid is just a coil of wire, but then creating an electromagnet from a solenoid by putting an iron core in the middle of it in the form of a nail or some other type of iron core. Then we talked about why electromagnets are good. So they can be turned off and on because they are only magnetized by electricity. So they can be turned off and on, we can make them stronger, we can make them weaker. And then finally, we went on to talk about the uses of electromagnets. So we talked about the crane picking up vehicles, the electric bell, the circuit breaker, and there was another one as well. So that kind of webinar yesterday is quite important in the understanding of today's webinar, which takes all of the concepts a little bit further. Okay, so we're going to start with the motor effect. Now, the motor effect is simply a conductor being placed in a magnetic field. Okay, so we already know that a wire carrying current has its own magnetic field. When you place that wire carrying current in an existing magnetic field, the magnetic field of the wire and the magnetic field that it's in exert a force on each other. Okay, so it's two interacting magnetic fields, magnetic forces, which kind of collide together and create a force. Okay, now that force is the motor effect. The reason it's called the motor effect is because it's to do with moving. Okay, so that wire is going to move, which is kind of a weird concept because nothing's actually touching it. The way that we know how objects move is by pushing or pulling a force with it, right? We can only move an object if we pull or push it. But with this wire carrying current, if you place it into a magnetic field, it will move by itself. Okay, so it's a non-contact force that we have there, and kind of a weird concept because it will just move by itself. Okay, so motor is to do with moving. Motor means moving, and that's how you remember the motor effect. Motor means moving. A conductor carrying a current, a wire carrying a current, moves in a magnetic field. Okay, so I'll just repeat the rule again. If you place a wire carrying current into an existing magnetic field, so the existing magnetic field is what we can see with the green lines here. The magnetic field of the wire, so remember the one that's circular around the wire, which we do with the right-hand grip rule, interferes with the existing magnetic field, and they collide together, they exert a force on each other, and that is what causes the wire to move and causes the motor effect. Okay, so it's all about this interaction of two magnetic fields. But which way does the wire move? Now this is really, really important and is all governed by Fleming's left-hand rule. So Fleming invented this rule. That's why it's called Fleming. It's not anything physical, it's just a guy. And this is how it goes. So you can hold up your left hand into, I don't know what shape you call that, like, I don't know. Anyway, so you've got your thumb facing up and you've got your first finger pointing out and your second finger pointing out, okay? Now your first finger and your second finger should be at right angles to each other, like this, so you can see it's like that. And then your thumb is pointing upwards. Okay, so that's how it's going to look. Now, what is represented by each finger? The thumb represents motion or force, the way in which the wire moves. Does it move up? Does it move right? Does it move left? Does it move down? So the thumb tells you the motion. The first finger is the magnetic field. So which way does the magnetic field point? Now remember, magnetic fields always go from north to south. So you can see on the diagram, there's north here and south here. So the guy is pointing his finger from north to south. Okay? Now the second finger is the direction of the current. Okay, so the direction of the current. And you can see here, the current is going through the wire from over here to over here. So our second finger points in that direction. Now, you're only going to know two of those quantities. You might know field and current and have to work out motion. You might know motion and field and have to work out current. So this is how you do it. You have the two quantities that you know. So let's say we're trying to find motion. We don't know that the wire is going to go upwards. We only know that the field goes from north to south this way, and the current goes from over here to over here. Okay, now by doing that with our first and second fingers, we automatically see that our thumb points upwards. Okay, our thumb points upwards without us having to do anything. We never put our thumb upwards, right? Just by simply having our first finger and our second finger in this position means that our thumb points upwards. However, if it were to be slightly different, so let's say now that our current was going from the top to the bottom. So I'm going to flip it like that. Now you can see that the motion is different. My thumb now points this way, to the right. Okay, so it really depends on those two quantities, and then your other finger or thumb will point in the way that will automatically point. Okay, hopefully that makes sense. Do have a practice with it. It is definitely a hard kind of concept to get your head around, and you can look quite crazy when you're doing it in an exam. But yeah, it's just all about having your fingers in the correct position, and then it kind of does the work for you, which is why it's such a great rule. Now, something really important to remember is it's always with the left hand. If you do it with the right hand, all your answers will be opposite, and we don't want that. Okay, so Fleming is always left hand, and Fleming is used for the motor effect. Okay, you only use Fleming if you want to know the direction of the magnetic field, or the direction of the current, or the motion. And most likely it's going to be the motion that you have to work out. The right hand grip rule is only used for finding which way the magnetic field rotates. Okay, so you have a current that goes in a direction, and right hand grip rule tells you which way round the magnetic field goes. Does it go anti-clockwise? Does it go clockwise? That's all right hand grip rule tells you. Left hand rule, Fleming's, tells you all about the motor effect. Okay, so don't get your hands mixed up. Okay, so going back to F equals BIL, which we talked about yesterday. So the force increases if the strength of the magnetic field increases, current increases, or length increases. Okay, and we can see that from the equation. So we have force. If we increase magnetic flux density, if we make B a bigger number, F gets bigger. Same thing, if we make I a bigger number, F gets bigger. L a bigger number, F gets bigger. So if any of these quantities increase, force increases. So how can we make our conductor move with more force? Well, we can increase the strength of the magnetic field, we can increase the current going through the conductor, or we can increase the amount of conductor that is in the magnetic field. So as you can see here, if we were to increase the length of the conductor in the magnetic field, that would provide a bigger force. Okay, so how does the electric motor employ the motor effect? Well, a coil of wire, which is this kind of square wire thing here, is allowed to move freely between two magnets. Okay, so you've got a north pole and a south pole. That's the magnetic field. The wire rotates round in that magnetic field when a current is put through the wire. Now, the direction of the current must be reversed every half turn, otherwise the coil comes to a halt again. So it flips round anti-clockwise, it gets to here, then it goes back, and it goes back, and it goes back. It never does a whole turn, okay? It gets reversed every half turn. And this is achieved using a commutator, okay? So you don't need to kind of know the ins and outs of a commutator. All you need to know is that the commutator is there so that it can keep in check the coil, okay? So making sure that the coil turns every half turn. That will make a little bit more sense later on when we look at AC and DC motors. Okay, so going on to looking at how the motor effect is used in a speaker. So speakers contain both a permanent magnet, which you can see here, and an electromagnet. Now, the two poles of the permanent magnet stay the same always. This could be a north, this could be a south. We know that permanent magnets never change, okay? The speaker has that magnet and that's it. Now, the electromagnet, however, reverses the direction of its poles, okay? So an electromagnet is in the speaker as well. Now, when the direction of the current reverses, the direction of the electromagnet reverses, the poles. Okay, so if we have constantly changing poles, the electromagnet is here, if it has constantly changing poles, you can see that it's going to attract, repel, right? Because if our electromagnet is like this, so if it's north and south match, it's repelling. But if our electromagnet poles get reversed, so we instead have south and north, you can see that it's going to attract. Yeah, so this attraction and repelling, this constant changing of attraction and repulsion, is what is allowing the speaker cone to vibrate. Okay, so the constant changing of the electromagnetic poles, and therefore the constant attraction, repulsion, allows the speaker cone, which is attached to the electromagnet, to vibrate. If the cone vibrates, then it vibrates the air in front of the speaker. Okay, so this is the cone vibrating and this is the air. Now, those vibrations of the air translate into sound, which we hear. Okay, so sound is just vibrations of air in a certain pattern, which allows us to hear music. So that is how the music gets from the magnets to your ear. So it's quite weird. You probably never thought of a speaker working like that, but it all uses this kind of switching of the poles and therefore this constant changing between attraction and repulsion. Okay, so moving on to the generator effect. So this is pretty different, okay? So this involves it's still a conductor in a magnetic field, but it's the moving of the conductor in the magnetic field. So the manual moving. In the motor effect, we didn't move the wire moved itself because of the magnetic fields interfering. In the generator effect, we have to move the wire or move the magnet. Okay, so the generator effect is all about generating current, generating electricity. Okay, so we're trying to generate current in a circuit. But to be able to create a current, we first need to have a voltage. The generator effect is all about inducing. Okay, inducing is a kind of a physics word for creating. Okay, so we induce a potential difference or a voltage. So the generator effect induces a potential difference, which is needed for current to flow in our circuit. Okay, so voltage is what allows current to flow. Now, this can be done either by moving the wire in the magnetic field, so moving it up and down, or in and out, or moving the magnet in the coil. Okay, so pushing the magnet in and out of the coil. So this is called electromagnetic induction or the generator effect. Those two names can be used interchangeably. If we move the wire in relation to the magnet or the magnet in relation to the wire, if there is movement between them, a current will flow. A potential difference will be created and a current will flow. Okay, so you can see that the ammeter detects this current being created. However, you can see on the ammeter there's a minus side and a plus side. So our current can change direction. It can go one way around the circuit or it can go the other way around the circuit. Whichever way around it goes determines whether it's a positive current or a negative current or a zero current. So how do we get each of those things? We know that there has to be movement of the wire or the magnet. If the wire or the magnet is not moving, if they're just sitting there, nothing's going to happen. Okay, nothing is going to happen because it's not movement. So if they're just sitting there, no current is going to be created. No potential difference will be induced. No current will be created. However, if you're moving the magnet in and out, or if you're moving the wire in and out of the magnetic field, current will be created. Which way that movement happens determines which way the current goes, so if it's positive and negative. So how can we change the direction of the induced potential difference or the induced current? So the thing that determines the direction of the current, so whether it's positive or negative, is the magnet being moved out of the coil, or the other pole of the magnet is moved into the coil. Okay, so it's really about when the magnet's being taken out and taken in, then you flip the magnet round and you put it in and out again, that's going to be different directions of current. Okay. How can we increase the potential difference that we're inducing? So this is all about changing the quantity of the potential difference that we're inducing. So these are about the direction down here. These are about the value, the quantity. So if the speed of the movement is increased, so if we're moving that magnet in and out of the coil really, really fast, we're going to get a higher potential difference, a higher current. We can also increase the magnetic field strength. Okay, so we can increase the power of the magnet. That's going to have an increased potential difference. The third thing that we can do to increase the potential difference that is being induced is have a bigger number of turns on the coil that we're pushing the magnet in and out of. So as I said yesterday, the reason that coils of wires are so good for creating a good magnet is because each of the magnetic fields of each of the little coils add up together. Okay, so instead of a straight wire which just has one plain small magnetic field, when we wrap that wire into a coil, each of the magnetic fields of each little coil add up together. So you can imagine that if we have more coils, we have more magnetic fields to add up. So our total magnetic field increases. And if our total magnetic field increases, our total induced potential difference increases. So 3 ways of doing that: speed, magnetic field strength, and the number of turns on the coil. Okay, so we know that the movement of the magnet in and out of the coil creates a current. So you can see on the left picture that the magnet is out of the coil and the current is 0. The magnet is not moving, so there's no current being created. Even if the magnet is inside the coil, it's still not moving, so there's no current being created. However, if the magnet is in the process of moving, in the process of going into the coil, we get a current, we get a positive current. Okay, so if we push the magnet into the coil, it's moving, right? If we're pushing it in, it's moving, and a current is created. But as soon as it stops moving, the current goes straight back to 0. So it needs this constant motion for a constant current to be created. Now you can see that the magnet going in creates a positive current. The magnet going out creates a negative current. So an induced current generates a magnetic field that opposes the original change. Okay, so the magnetic field opposes the original change. So we've pushed the magnet in this way, from left to right. So that means the magnetic field created by the current goes from right to left. Okay, if we were taking it back out, the change is from right to left. So the magnetic field is from left to right. Quite a complicated rule, but all that it means is that whichever way you push the magnet in or out determines the magnetic field that is created because of current flowing through the wire. Okay, so how do we apply this generator effect to the AC generator? Okay, so the AC generator is all to do with alternating current. Now, if you remember all the way back to the electricity webinars, we talked a little bit about AC current and DC current. AC is alternating current or alternating potential difference. Alternating current is this idea that the current constantly changes direction. It goes from positive to negative constantly. Now, this all is determined by which way the coil of wire rotates in the magnetic field. So, in the diagram, we can see that the coil is rotated in the magnetic field. Current is then induced in the rotating coil. So remember, if a conductor is moved in a magnetic field, current will be induced. The slip rings connect to the coil and the brushes make continuous contact between the external circuit and the slip rings, which allows current to flow. So all that the slip rings do is kind of complete the circuit. But it's this idea that we have a conductor, or the coil of wire, the square wire, moving in a magnetic field, which means that current is induced. Okay, now because it is doing a whole turn, it's constantly turning, the current is going to constantly change direction. Okay, a weird concept, but if the coil of wire is allowed to do a full rotation, the current constantly changes between positive and negative, which we can see here in this graph. So the current or the voltage, either or, constantly changes from positive to negative. So you can see that it's going from 0, positive, back to 0, negative, back to 0 over time. Okay, so that current is constantly changing direction because it is allowed to rotate fully in the magnetic field. Now we're going to compare that to the DC generator. Now the DC generator only allows the coil of wire to do a half turn. Okay, so that's what we saw earlier on in the webinar. If the coil of wire is only allowed to do a half turn, so it goes like this, constantly changes direction, then we're only going to get a DC current. Okay, so the wire does a half turn, then it's reversed, then it does its half turn, then it's reversed. This means that the current stays in one direction. Okay, so before our wire was allowed to do a whole turn, and therefore that meant that the current changed between positive and negative and positive and negative. But in the DC generator, the direct current, it flips every half turn. It's not allowed to do a whole turn anymore. It does a half turn and it's reversed. And this means that current is only in one direction. As you can see, it's only positive on the graph, right? It never goes to the negative part of the graph if this is 0. Okay, so the current is only positive. So it still provides a potential difference, but it's a positive one. Okay, still has a coil of wire rotating in a magnetic field, but our split ring commutator, okay, that's this bit here, split ring commutator, means that it only allows the coil to do a half turn. Okay. Hopefully that makes sense. I know it's been some quite complicated concepts that we've gone over today. So if you do have any questions, please do put them in the chat. You can even submit them anonymously if you want to. Okay, so finally we'll talk about microphones. So microphones convert sound waves into electrical signals. Okay, so we know that, that's why we hear the sound of, for example, on karaoke, if you're singing into a microphone, sound waves from your mouth, the vibrations of the air from your mouth, go into the microphone. Once they're in the microphone, those sound waves get translated into electrical signals, which go into the speaker and allow us to hear sound again come out of the speaker. Okay, so microphones use the generator effect to induce a change in current from the pressure variations of sound waves. Okay, so here's a diagram to support this explanation, and it's quite a long description and long process of how microphones work, and it is worth bearing in mind that this is higher tier for AQA. Okay, so pressure variations in sound waves cause the diaphragm. The diaphragm is this bit here, the surface here, okay, to vibrate. That's the first thing that happens. So there's a diaphragm in the top of the microphone that detects these sound waves and vibrates to the sound waves. So it matches the vibration of the sound waves. Okay, so pressure variations just means when you're getting louder, when you're getting quieter, when you're getting higher pitched, when you're getting lower pitched. So you're singing into that microphone, which creates pressure variations in sound waves. Louder, quieter, high pitched, lower pitched. This then causes the diaphragm to vibrate. The diaphragm is just a surface that vibrates in the same way that the sound waves do. Now, those vibrations in the diagram create vibrations in the coil. Okay, so you can see the coil here. This is an electromagnet. The coil moves relative to a permanent magnet. So remember, we're going back to the same concept. If a coil moves in relation to a magnet, or if a magnet moves in relation to a coil, we get a voltage induced. We create a voltage, we create a current. Okay, that's the whole point of the generator effect, is to create electricity. Yeah, generate electricity, generate a voltage, generate a current. And it's all done by this relative movement between the magnet and the coil of wire. Okay, so there needs to be this movement between the coil of wire and the magnetic field or the magnet. And there is. The coil is vibrating in relation to the magnet. So we get a potential difference induced. Now that coil is part of a complete circuit. So that means that the voltage has somewhere to go. The voltage can travel, the current can travel in that circuit. Now the changing size and direction of the induced current causes, so the changing size and the direction of the induced current matches the vibrations of the coil, which matches the vibrations of the sound waves. Yeah, so the changing size and direction of the current matches the vibrations of the sound waves. Now those electrical signals that are generated in the circuit match the original pressure variations of the sound waves and can be amplified back out as sound waves again. Okay, so it comes full cycle. The sound waves have pressure variations that cause the diaphragm to vibrate. The vibration of the diaphragm causes vibrations in the coil. Because that coil is now moving in relation to the magnet, we get a current created, we get a voltage created. Because that coil is part of a full circuit, the current and the voltage have somewhere to go. Yeah? So now that the current is traveling through the circuit, the changing size and direction of the current matches those original vibrations. Now, we're going to get various kind of different sizes of current, different directions of current, which make for different sounds. High-pitched sounds, low-pitched sounds. Loud sounds, quiet sounds. Okay, so it's really kind of an amazing concept, taking sound waves that vibrate a coil in relation to a magnet, which creates electricity, which is then changed back into sound waves. Okay, so a quite important application, and one that you do need to know the process of off by heart. Okay, so that brings us to the end of our content. I'm just going to take a few questions now before we do move on to our quick fire questions. Okay, when you make electricity, do we have to move the wire for the magnet to work? Yes. So if you are talking about the generator effect, if you want to create a voltage, if you want to create a current, you have to move the wire. Okay, you have to move the wire for the magnet to work and create electricity. If you have more coils, does that mean that the field would get stronger? Yes, absolutely, that's completely correct. If you have more coils of wire, there's more magnetic fields to interact, so they can all add up to create a bigger magnetic field overall. If the coil stops moving, is the voltage lost? Yes. So if there's no movement between the magnet and the coil, no current is being created. No voltage, no current is being created. It's only if they're moving constantly is voltage, is current created. Okay, so let's go on to our quickfire questions now. What is another name for electromagnetic induction? And how can the direction of an induced potential be reversed? And how is contact between the coil and the circuit maintained in an alternator? Okay, so what is another name for electromagnetic induction? So if we go back to the motor effect, where's the slide? Okay, so the generator effect is what is known as electromagnetic induction. How can the direction of an induced potential be reversed? What can we do? Okay, so by changing the direction of the magnetic field only, we reverse the induced potential. If we reverse both the direction of the magnet and the magnetic field, that kind of cancels out and it does the same thing that it was originally doing. So you only change one to get the potential to be reversed, to get the current to be reversed. Okay, so only changing one. Don't change both, because that would just be the same thing that you had originally. How is contact between the coil and the circuit maintained in an alternator? What happens? So slip rings and brushes allow continuous connection. Okay, so continuous connection. It's allowed to do this full term. Okay, how can the potential difference output from an alternator be doubled? Should we double the speed? Should we reverse the direction of rotation? Or should we halve the speed of the rotation but reverse the direction? What do you think? So how can this output, this voltage, be doubled? Okay, so all we do is we double the speed. If we double the speed of rotation, we double the voltage being created. The direction has no effect on this. It's all about the speed. Doesn't matter what the direction of rotation is. If you increase the speed, you increase the potential difference. Okay, how can the potential difference output from a dynamo be doubled? A dynamo is just a more fancy word for the DC motor. So the second motor that we looked at, how can we double the potential difference? So it's the same thing again. If you double the speed of the rotation, you double the potential difference. Okay, so that really is the only rule that we have. If the direction has no effect on increasing the voltage from the motor. Okay, how does a moving coil microphone create electrical signals? Does the magnet vibrate inside a coil of wire? Does the coil of wire vibrate in the magnetic field? Or does an electromagnet vibrate inside of a coil of wire? Quite similar answers there. To be specific, so it's really all about this coil of wire vibrating in the magnetic field. Yeah, the vibrations of the diaphragm cause the vibrations of the coil of wire. That coil of wire is sat in a magnetic field. Okay, so this is a typical GCSE question. You're going to see something that you've probably never seen before. And that can be quite a scary concept in a GCSE, but it's one of the things that they've introduced to make the GCSEs a little bit harder. So you need to be able to apply your knowledge of electromagnetism and motors to talk about how this ignition circuit works. Okay, so I'm just going to give you a minute to brainstorm some ideas, have a think, look at the components of the circuit, think about what this might be similar to that you've seen before, and how it might work. So just give you a minute to think about it. Put some ideas on the chat if you want, talk with each other on the chat if you want. Just have a think. So closing the switch causes a current to pass through the circuit. We know that, right? As soon as we close the switch, we complete the circuit and the current can flow. It has somewhere to go. If that switch is closed, a current flows through the wire, the coil of wire. Now, if current flows through the coil of wire, the electromagnet comes to life. The electromagnet gets magnetized. Now, if the iron core of the electromagnet becomes magnetized, that iron core is a magnetic material, which means that it also attracts the short side of the iron arm. Okay, so the electromagnet has now become magnetized, which means that this bit here is attracted to this surface here. So they're going to touch. Now, if you think about the way that the pivot works, if this bit goes down, this bit comes out, right? They're connected on a hinge. Yeah, so if this bit goes down because it's attracted by the magnet, the electromagnet goes down, so this bit goes up. So this long side gets kind of kicked out, right? It gets kicked out to the right because this moves down. Now you can see that that's going to hit these contacts and make them, force them together. Yeah, so this iron arm hits the motor contacts and puts them together. Now, if they become in contact with each other, they create a little circuit of their own. So you can see that it's like a mini circuit inside our circuit. So it goes from here, contacts hit, and then it goes into the motor. So because those contacts come together, that mini circuit is completed. Okay, so those touch and the starter motor therefore gets the current flowing through it. And if the current goes through the motor is allowed to turn. And that's how this circuit works. So breaking down a circuit and really thinking about what each component does, and just kind of taking a step back from all the physics and just kind of using what's more mechanics and common sense to work out how a circuit works is quite a common question in the GCSE. Okay, so we'll just go through it again quickly. The switch is shut. Okay, so someone flicks a switch and that creates a complete circuit. Because there's a complete circuit, there's a current flowing through the circuit. That current goes into the coil of wire. If there's a current flowing in the coil of wire, the electromagnet comes to life. That iron core of the electromagnet becomes magnetized. Okay, it wasn't a magnet before. when we put a current through it, it becomes an electromagnet. Now, because it's magnetized, it's going to attract the iron arm. Now, because the top of the iron arm comes down, it kicks the other arm out. Okay, so it kicks it out to the right. And we know that because of how a pivot works. So if we put a force on the top of the pivot, it kicks it out to the right. Now, because it kicks it, that hits those contacts. If those contacts come together, they create a full circuit. Now, we have a second kind of mini circuit within our circuit, which is completed by these contacts. If that little mini circuit is completed, a current flows through that circuit as well. And if a current flows through that circuit, it flows through the motor. And if a current flows through the motor is allowed to turn. So it's this chain reaction of lots of different things, which is really what all the processes in the last 2 days have been talking about. Yeah, so a chain reaction. Something happens, something else happens, something happens, something else happens. So it's all about processes in the generator and motor effect. Okay, that's been cut off, so we won't do that one. Okay, so going back to Fleming's left-hand rule, let's see if you can remember what the first finger means and what the second finger means. So put your answers on the chat. What does the first finger represent and what does the second finger represent? And then I'm going to show you a cool way to remember it. Okay, so the first finger is the direction of the field. And the second finger is therefore the direction of the current. Yeah, direction of the current. Okay, so the way that we kind of say to remember it is that first finger begins with an F and so does field. Second finger is a bit of a stretch, but there's a C in second, so they kind of match. So second, the C in second matches the C of current. Then finally, how to remember the thumb one? Well, if we write thumb and we say instead of the direction of the force, we just call it motion, same thing. Then you see that the M and the M match. So it is kind of a long way to get there, but if you kind of get that the first is the field, then everything kind of comes from that. Yeah, so you only have kind of two choices, and we know that the thumb is the direction of the force and the current is the second finger. The most important thing with Fleming's left-hand rule is that you do use your left hand and that you have the right angle here. Yeah, so you're not like putting this parallel, this is also a right angle. So your first finger and your thumb should be at right angles, and your first finger and your second finger should be at right angles. Yeah, so we get this shape. Okay, so we have a coil of wire moving in a magnetic field. So remember, if a coil of wire or a conductor moves in a magnetic field, that creates a potential difference which drives a current. Now the arrows labelled F show the direction of the forces acting on the side of the coil. So you can see that it's going in a kind of clockwise direction. Describe the motion of the coil until it comes to rest. So what happens to that coil? What happens to that coil? So the motion of the coil experiences this clockwise force. Yeah, so it turns clockwise and it oscillates. Okay, so it turns clockwise, 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 clockwise until it's facing the South Pole. Then it reverses and it goes anti-clockwise till it's facing the North Pole. And it keeps doing this reversing, but at each pole it comes to rest. So it goes clockwise till it faces a pole, comes to rest and reverses, comes to rest and reverses, comes to rest and reverses. Okay, so this is going back to what we were talking about earlier. When a conductor carrying an electric current is placed in a magnetic field, the force acts on it. Yeah, so we're not touching it. It's because of this interaction of the magnetic field of the conductor of the wire and the existing magnetic field that interacts with each other and create this force. That's the motor effect. Now, how can we increase this force? What do you think that we could do to increase this force? So it's really going back to F equals BIL, which is the equation that we have for a conductor in a magnetic field. So we know that to increase the force, we can increase the current or we can increase the magnetic field strength. Yeah, so increase the current or increase the magnetic field strength. Other appropriate answers would have been increase the voltage going through the circuit, which would increase the current. So it's kind of a different way of saying increase the current, but you should try to say increase the current, not increase the voltage. You could say reduce the resistance. You could also say have thicker wiring. So that's increasing the amount of wire that's in the magnetic field. Or even saying to have more cells. So over here, have more cells. So lots of answers that you could have had. Could even have said have stronger magnets. However, the main ones and the ones that kind of come from the equation that we've talked about, F equals BIL, is to increase the current or increase the magnetic field strength. Okay. So I think we'll stop there. That's brought us to the end. And I don't think there's any more questions. So
just had a quick look as well. I don't think there's any more questions, and I think we've kind of run out of time for today's session. So thank you so much to everyone for joining and for sticking around, and remember it is recorded, so you'll be able to watch it back when you'd like to, and also if you're sticking around, then we have our English session at 11 o'clock this morning. Thanks everyone, see you soon, bye.
Bye.